Welcome to the Deep Dive, where we crack open complex subjects and pull out the essential insights you need to be truly well-informed. You likely interact with artificial intelligence and machine learning every single day, often without even a second thought. Think about your streaming service suggesting your next binge watch, or your phone instantly understanding your voice commands. AI and ML are, well, they're everywhere, making our lives surprisingly efficient.
Oh, absolutely. They're foundational to modern digital life now, woven into experiences we just take for granted. It's really quite remarkable how far the field has come and how quickly.
And that's precisely what we're going to uncover today. We're taking a deep dive into that fascinating world. We'll start with the broad strokes of machine learning, then zoom in on its incredibly powerful subset, deep learning. And finally, we'll shine a bright spotlight on the revolutionary transformer architecture that underpins so many of today's most advanced AI systems.
Yeah, our mission today is really to demystify these concepts. We want to show you their fascinating evolution, explain how they actually work, highlight their, truly widespread applications, and frankly, have an honest discussion about the significant challenges and the ethical considerations they bring up. We've pulled together insights from a stack of detailed sources, academic analyses, encyclopedic overviews, just to give you the clearest, most comprehensive understanding possible.
Right, so whether you're prepping for a crucial meeting, keen to catch up on a cutting-edge field, or maybe you're just immensely curious, this deep dive is designed to give you those aha moments, without getting bogged down in impenetrable jargon. Okay, let's unpack this. Let's start right at the beginning with the foundation. Machine learning ML. For someone who hears the term all the time but isn't quite sure what it means, how would you define it?
Okay, so at its heart, machine learning is a branch of AI where computers don't just follow explicit instructions like traditional programming. Instead, they learn directly from data and improve their performance over time. There's a classic definition. A computer program learns from experience E with respect to some class of tasks. T and performance measure P if its performance at tasks in T, as measured by P, improves with experience E.
Okay, that sounds a bit academic.
It does, yeah. But what it essentially means is the more data it sees, the experience E, the better it gets at a specific task T, measured by P. Simple as that, really.
Right, I like that breakdown better. So if I want a computer to identify a cat in a photo, instead of me writing out a list of rules like a cat has pointy ears, whiskers, and so on, I just show it thousands of pictures, some with cats, some without, and it figures out the distinguishing patterns itself. Is that the basic idea?
Exactly. You feed it the data, and the algorithms work to find hidden patterns and correlations within that data. And crucially, like you said, the more data available, the more accurate and robust the application typically becomes. It's almost intuitive, isn't it? Like the more examples a human student sees, the better they grasp a concept. Machines are sort of similar in that respect.
That makes a lot of sense. Now, I know there isn't just one type of machine learning. It's not a one-size-fits-all approach, right? Can you walk us through the main categories?
Absolutely. There are three primary ways machines learn. First up, we have supervised learning. Imagine you have a teacher providing the answers. In this scenario, the model is given labeled data. That means we provide both the known inputs, like an image, and their corresponding correct outputs, like this is a cat.
Okay.
The model then learns the relationship, the mapping between them, so it can predict outputs for new unseen inputs. So if you've ever had software classify an email as spam or seen a system predict housing prices based on past sales data, that's supervised learning in action.
So, it's learning from examples where the right answer is already known.
Got it. But I imagine there are countless real-world scenarios where you don't have those perfectly labeled data sets. Labeling data is expensive, right? So how do these powerful systems learn when there's no clear right answer being fed to them? What happens when there's no teacher?
That's precisely where unsupervised learning becomes so valuable. With this type, the model works with unlabeled data. No known outputs are provided. The goal isn't really to predict a specific answer, but rather to discover hidden patterns or inherent structures within the data itself. Think about a streaming service grouping its users into different taste clusters without anyone telling it what those clusters should be beforehand.
Like finding natural groupings.
Exactly. Or a system detecting unusual, potentially fraudulent transactions that just don't fit any normal pattern it's seen. It's about finding order in the chaos, you could say.
Fascinating. So it's more about discovery than direct instruction.
Okay.
And the third type, I've heard of systems learning to play games like chess or Go and becoming absolute masters. Is that related? You're thinking of reinforcement learning. This is where the model learns by interacting directly with an environment. It receives rewards or penalties based on its actions. So it tries something, gets feedback, and adjusts. It continuously refines its behavior to maximize those rewards over time, working towards a specific goal. The classic examples are indeed programs learning to play complex games like Go or chess. They learn winning strategies through literally millions of rounds of trial and error. They get a reward for good moves and a penalty for bad ones. It's an incredibly powerful way for machines to develop complex strategies, almost like learning through experience.
Right, trial and error on a massive scale. Okay, so if machine learning is this broad foundational field, let's peel back another layer. What about those truly breakthrough moments we're seeing today, like the powerful AI behind the latest creative text generators? Many of them wouldn't exist without what's often called ML's powerful younger sibling, deep learning. So what precisely makes deep learning deep?
Good question. Deep learning, or DL, is a subset of machine learning that specifically uses artificial neural networks, ANNs. The deep part refers quite literally to the number of layers in these networks. Think of it like processing information through many successive filters or stages. Data enters an initial layer, gets transformed by one hidden layer, then another, and another, sometimes hundreds deep. Each layer extracts more abstract and complex features from the data passed by the previous one.
So more layers equals deeper understanding, potentially.
That's the idea.
Yeah.
A substantial credit assignment path, or CAP depth, typically more than 2 layers. More layers help extract better, more hierarchical features.
I've always found the neural network concept intriguing because it sounds like it's mimicking the human brain. Is that the primary goal or even a good analogy anymore?
Well, early ANNs were certainly inspired by the structure and information processing of the human brain, yes. But current neural networks don't primarily aim to model biological brain function. They're generally seen as pretty low-quality biological models, actually. Their immense power comes more from their mathematical structure, the layered processing, and their ability to find intricate patterns in vast amounts of data, rather than any direct biological mimicry. It's more engineering than neuroscience these days.
Okay, makes sense. So focusing on that structure then, what does it look like? What are the key components of one of these deep neural networks?
A deep neural network, or DNN, typically has 3 main types of layers. You have the input layer, pretty straightforward, where the raw data, say the pixels of an image or the words in a sentence, enters the network. Then there are multiple hidden layers. Sometimes, hundreds, as we mentioned, nestled between the input and output. This is where the real complex processing and feature extraction happen. Each hidden layer transforms the data from the previous layer into a progressively more abstract representation. Finally, the output layer produces the network's final prediction or classification, like this image contains a cat, or the sentiment of this text is positive.
It sounds like a very complex pipeline, processing things in stages. It's impressive. Let's trace the journey of deep learning a bit. It wasn't always this prominent, was it? You mentioned earlier we went through what some call AI winters.
Not at all, no. Its history is a really fascinating story of ingenuity, setbacks, and then eventual triumph. The early seeds were planted well before the 1980s. You had concepts like the Ising model back in the 1920s looking at statistical mechanics, and even early ideas about recurrent neural networks. There were precursors to today's powerful systems, like the neocognitron in 1979, which was an early type of convolutional neural network designed for pattern recognition. But the crucial breakthrough for actually training these networks efficiently, an algorithm called backpropagation, well, its mathematical roots go back centuries to Leibniz's chain rule in the 17th century, but it only really gained popularity and widespread application for neural networks in the 1980s, particularly with research published around 1986.
So the 80s and 90s saw some initial growth, applications like recognizing handwritten digits you mentioned,
Yeah.
but then a lull. It sounds like there was a hidden problem that kept them from truly taking off back then.
Precisely. The 1980s into the 2000s were a period of exciting growth initially, but then came a significant AI winter, a period of reduced funding and interest. We saw remarkable early applications, absolutely. Convolutional neural networks, CNNs, were applied to tasks like phone and alphabet recognition in the late 80s. Jan LeCun's-Linnet in 1989 famously recognized handwritten ZIP codes, pretty amazing for the time, and was even adopted by banks for reading checks in the late 1990s. Recurrent neural networks, RNNs, were also further developed for processing sequences like speech or text. But despite these promising signs, a major obstacle emerged in the early 90s, the vanishing gradient problem.
The vanishing gradient, right. What exactly was that, and why was it such a significant hurdle? Why did it stall things?
It was a critical challenge. When you train these deep networks, the error signals used for learning have to propagate backward through all the layers, from output to input. With vanishing gradients, these crucial error signals would essentially shrink and shrink, getting exponentially smaller as they move back through the network. So the earlier layers, the ones detecting basic features, would learn extremely slowly. Or just. Not at all.
Ah, like the feedback signal just died out before it reached the layers that needed it most.
Exactly. It was like trying to send a message across a very long chain, but the message kept getting fainter and fainter until it was completely lost near the start. This made training truly deep networks practically impossible for a while.
Okay, so how was that massive problem addressed? Was there a clever workaround or a new invention?
A truly significant breakthrough came with long short-term memory networks, LSTMs, invented back in 1995 by Sepp Hochreiter and Jürgen Schmidhuber. LSTMs were specifically designed with internal memory cells and gates to control information flow. This architecture explicitly aimed to overcome the vanishing gradient problem. It allowed networks to learn and remember information over long sequences, dependencies across thousands of time steps, which was impossible before. This was a real game changer.
Wow, 1995. That's earlier than I would have guessed.
Yeah, the ideas were around. LSTMs became competitive in speech recognition by 2003 and started winning pattern recognition contests. However, despite these advancements, neural networks still faced that period of reduced interest in the 1990s and early 2000s. It was largely due to the high computational costs they needed, a lot of power, and perceived complexity compared to simpler, more understandable models like support vector machines. But the resurgence really began around 2006. New techniques like deep belief networks helped reignite interest, and crucially, this coincided with ever-growing computational power, particularly from GPUs, and the availability of vast amounts of data from the internet.
That sets the stage perfectly for what happened next. The deep learning revolution and the emergence of transformers. This is where things really took off, and the AI we see everywhere today began to emerge. What fueled this explosion of capability in the early 2010s? You mentioned GPUs.
The revolution truly took hold then, yeah, and it was primarily fueled by massive advancements in hardware. Specifically, graphics processing units, GPUs. Originally designed for rendering complex graphics in video games, researchers realized they were incredibly effective at the parallel computations needed for deep learning training. Matrix multiplications, basically. An early demonstration in 2009 showed GPUs speeding up deep learning training by up to 70 times compared to traditional CPUs.
70 times. That's huge.
It was transformative. Then, specialized AI processors like Google's TPUs, tensor processing units, and Huawei's NPUs emerged, designed specifically for AI workloads. Just look at the scale. The amount of computation used for the leading AI projects increased a staggering 300,000-fold between 2012 and 2017.
300,000. It's almost hard to comprehend that scale of increase.
It really is. It's like going from a horse and buggy to a supersonic jet in just 5 years. This computational horsepower was the absolute game changer. It allowed us to train networks so vast and complex they were previously unimaginable.
And that massive increase in power directly led to some pretty famous breakthroughs that made headlines, didn't it?
Absolutely. The progress was rapid and very visible. In 2011, a CNN achieved superhuman performance in a visual pattern recognition competition. Then in 2012, a deep neural network famously learned to recognize high-level concepts like cats just by watching unlabeled YouTube videos, a huge feat of unsupervised learning. Later that same year, the AlexNet CNN won the ImageNet competition, a benchmark for image recognition, by such a significant margin that really kicked off the modern deep learning revolution in computer vision. And of course, a landmark moment for the public perception of AI was in 2016 when Google DeepMind's AlphaGo system using deep reinforcement learning famously beat Lee Sedol, a world champion Go player.
Right, AlphaGo was massive news.
Huge. And on the technical side, things kept improving too. Techniques like residual neural networks, or ResNet, developed in 2015, helped overcome challenges in training very deep networks. We're talking 20, 30, even over 100 layers without their accuracy degrading, which had been another problem. The impact was tangible. By 2015, Google reported that their speech recognition accuracy had improved by nearly 50% thanks to using deep LSTM models. Progress was fast.
So we had powerful hardware, larger data sets, and deeper, more robust network architecture like CNNs, LSTMs, and ResNets. And then in 2017 came this paper, Attention is All You Need, introducing the transformer architecture. This was another true game changer, right? What made it so revolutionary, especially for language?
The transformer was and is revolutionary. Introduced in that 2017 Google paper, it fundamentally changed how we model sequential data, particularly natural language. Its key advantage over previous recurrent networks like RNNs and LSTMs is that it does not process data sequentially, one step at a time. LSTMs still had to read word by word, essentially. Transformers use a mechanism called self-attention, or more specifically, multi-head attention, and they can process entire sequences in parallel.
In parallel. So he can look at an entire sentence or even a whole paragraph at once, rather than just processing word by word from start to finish.
Exactly. Think of RNNS LSTMs like a single person reading a very long book word by word, painstakingly keeping track of context. Transformers are more like a whole team of people reading all the pages simultaneously, instantly connecting ideas and references from anywhere in the book to anywhere else. This parallel processing was crucial for training on the absolutely massive datasets needed for modern large language models. It drastically sped up training times and allowed models to capture long-range dependencies much more effectively.
Okay, that parallel processing and attention sound like the core ideas. How does it actually do that? What are its core components that enable this kind of simultaneous understanding?
Right, let's break it down. First, you have tokenizers. These convert the input text into numerical tokens, basically, numbers representing words or often parts of words. Then, an embedding layer. This transforms these numerical tokens and their position in the sequence into rich vector representations. These vectors capture semantic meaning. And position is key here. Innovations like rotary position embedding, rope, or attention with linear biases, alibi, are clever ways the model encodes where each token is in the sequence because, dog bites man means something very different from man bites dog.
The order matters.
Yes.
Hugely. Okay, so you have these rich vectors representing words and their positions. What happens next?
These embedded vectors then pass through a stack of identical transformer layers, sometimes dozens, even hundreds of these layers. Each layer has two main subcomponents. The first is the multi-head attention mechanism. This is the real heart. It learns three sets of weights called query, key, and value for each token. Think of it like this. For every word, query, the attention mechanism calculates a score based on how relevant every other word, key, is to it. These scores then determine how much attention or weight is given to the information, value, from those other words when updating the representation of the current word. Multi-head just means it does this multiple times in parallel, focusing on different kinds of relationships simultaneously. Maybe one head focuses on grammar, another on semantic meaning, etc.
So it's constantly calculating how every part of the input relates to every other part regardless of distance.
Precisely, regardless of distance. That's the key difference from RNNs, which struggled with long distances. Then, within each transformer layer, there's also a feed-forward network, just a standard neural network layer for further processing of each token's representation independently. And crucially, things like residual connections, adding the input of a layer to its output, and layer normalization are used throughout. These are vital for stabilizing the training of these very deep networks and avoiding issues like vanishing gradients again.
It's an intricate dance of components. And what about generating text, like these large language models we interact with? How do they ensure the generated text actually flows logically and makes sense?
For generation, especially in what are called decoder models, a mechanism called masked attention is crucial. When the model is predicting the next word in a sequence, masked attention ensures it can only attend to the words before it in the sequence, not the ones that come after, which it hasn't generated yet. So when it's generating word number 5, it only looks back at words 1 through 4. This forces it to generate text sequentially and realistically, like humans do.
Makes sense. It can't cheat by looking ahead. Okay, I've also heard about models being pre-trained and then fine-tuned. What does that two-step process mean in the context of transformers?
That refers to the pre-train fine-tune paradigm, which has become the standard practice, especially for large language models built on transformers. First, they are pre-trained on absolutely massive, usually generic datasets, often just unlabeled text scraped from the internet. During pre-training, they use self-supervised learning tasks like predicting masked words or the next sentence to learn general language patterns, grammar, facts about the world, reasoning abilities, etc. They build a broad understanding. Then, this powerful pre-trained model is fine-tuned on a smaller, more specific, often labeled dataset, tailored to a particular task you want it to perform, like translation, summarization, question answering, or even chatbot interaction. This two-step process is incredibly efficient. You do the hugely expensive pre-training once, and then you can adapt the model relatively quickly and cheaply to many different downstream tasks.
So it's like getting a broad university education first, then specializing in a specific field.
That's a great analogy, yes.
And are all transformers built the same way? Or are there different architectural flavors depending on the task?
There are three main architectural variations based on which parts of the original Transformer paper's design they use. Encoder-only models, like the well-known BERT model, use only the encoder stack. They are really good at tasks that require understanding the input text deeply, like text classification or generating dense vector representations, embeddings of text for search. Decoder-only models, like the very popular GPT series, GPT-2, GPT-3, GPT-4, and models like Chinchilla, use only the decoder stack with that masked attention we talked about. They excel at generating coherent text, following instructions, and conversational AI. And then there's the original full encoder-decoder architecture, which uses both stacks. This is common for sequence-to-sequence tasks like machine translation, translating from an input language sequence to an output language sequence, or text summarization. The T5 series of models is a good example here.
Okay, different tools for different jobs. Now, with all this complexity and the need for massive data sets and computation, efficiency must be a huge challenge. Are there innovations to make these models faster or more practical to run?
Definitely. The computational demands are immense, especially for the largest models, so efficiency is a constant focus of research. One interesting technique is speculative decoding. This aims to speed up text generation, which can be slow because it's often sequential, generating one token at a time. The idea is to use a smaller, faster draft model to generate a chunk of speculative future tokens, and then have the larger, more accurate model quickly verify or correct that chunk in parallel. If the draft is mostly right, you save a lot of time compared to generating token by token with the big model.
Clever.
Cool.
Like having a junior assistant draft something quickly for the senior expert to review.
Kind of, yeah. There's also significant ongoing research into subquadratic transformers. The standard attention mechanism has a computational cost that scales quadratically with the input sequence length. Double the input length, and the computation roughly quadruples. This makes it very expensive to process very long documents or conversations. Subquadratic approaches aim to change that scaling to be closer to linear, making it feasible to handle much larger contexts without the computational cost exploding.
That could open up a lot of possibilities for understanding longer texts or dialogues. So it's not just about text anymore, right? We're seeing transformers move beyond words and into understanding images or even speech. How does that leap from text to other modalities actually work?
That's a key development, this push towards multimodality. The core idea is always finding a way to tokenize the other types of data, to break them down into sequences that the transformer can process, just like text. For computer vision, the dominant approach now is vision transformers, VITs. They break an image down into a grid of small patches, treat each patch like a token, embed them, along with position information, and feed them into a standard transformer encoder. It turns out this works incredibly well for image classification and other vision tasks. For speech recognition, models like Conformer, which blends transformer ideas with convolutions, and OpenAI's Whisper often convert the raw audio waveform into a spectrogram, which is basically a visual representation of the sound frequencies over time. Then they process that spectrogram kind of like an image, often breaking it into patches too. And looking even further ahead, there are architectures like Google DeepMind's Perceiver and Perceiver IO, which are designed from the ground up to handle many different data modalities, text, images, audio, even point clouds or video using a shared attention mechanism. The goal is a single, flexible architecture for general perception.
It's truly fascinating how adaptable that core transformer idea has proven to be. Okay, so let's talk about the real-world impact. Where are we seeing machine learning, deep learning, and especially transformers in action today, shaping our daily lives?
Their applications are truly pervasive and growing constantly. In automatic speech recognition, ASR, deep learning models, particularly LSTMs historically, and now increasingly transformer-based models like Whisper, power the voice assistants you use every day, Siri, Alexa, Google Assistant, and make transcription services remarkably accurate. Natural language processing, NLP, has been completely transformed. Machine translation, like Google Translate, handling over 100 languages by learning sentence semantics directly, relies heavily on encoder-decoder transformers. Text summarization, realistic text generation, like ChatGPT, sentiment analysis of customer reviews, it's all driven by these models.
So when I use Google Translate or talk to a chatbot, I'm essentially interacting with a transformer-based system. That's incredible. What about visual applications or even going beyond language and images?
In computer vision, deep learning, especially CNNs and now vision transformers, is used for everything. Image classification recognizing objects, people, scenes, facial recognition, medical image analysis for detecting tumors or other anomalies in X-rays or MRIs with increasing accuracy, and even generating incredibly realistic, sometimes unsettlingly realistic, images using generative adversarial networks, GANs, or diffusion models. Beyond these common examples, the impact extends deeply into scientific and industrial fields. We're seeing it used heavily in drug discovery and toxicology, helping to accelerate the identification of promising new drug candidates and predict their potential effects or toxicity much faster than traditional methods. In autonomous vehicles, deep learning is absolutely essential. It enables self-driving cars to perceive and understand their complex environment, identifying pedestrians, other cars, traffic lights, lane markings, and make critical real-time driving decisions. Even in niche areas like military applications, robots are being trained using reinforcement learning to learn new tasks simply through observation and feedback.
And it doesn't stop there, does it? I've heard about significant scientific breakthroughs being powered by this technology as well.
Absolutely. They're becoming fundamental tools in science. They're being used for solving complex equations. For instance, physics-informed neural networks, PINNs, are helping to approximate solutions to challenging partial differential equations in physics and engineering. In climate science, deep learning models are now learning skillful medium-range global weather forecasting, sometimes even outperforming traditional physics-based models for certain tasks. In biology, epigenetic clocks, which aim to measure biological age rather than chronological age, now often use deep neural networks trained on methylation data from blood samples to achieve high accuracy. Even in the realm of gaming and strategy, systems like AlphaGo for Go, AlphaZero, which taught itself chess, shogi, and Go, and others that evaluate complex game positions demonstrate clear superhuman performance, changing how humans approach these games. And of course, there's widespread commercial use everywhere. Automated image tagging on social media platforms, content moderation systems trying to filter harmful content, recommendation engines predicting what you'll buy or watch next, AI-powered quality control systems in factories, optimizing logistics routes, the list just goes on, and the sheer scale and breadth of impact are truly staggering.
It's easy, maybe too easy, to get swept up in the sheer, undeniable power and potential of these technologies. They are achieving amazing things. But as we've seen throughout history with any transformative tool, there's always a dual nature. There are always risks and downsides. And this is where our deep dive pivots to something critically important: the profound ethical considerations and the significant challenges these technologies force us as a society to confront. This is where the real complexity and, frankly, the future direction lies.
Indeed. It's absolutely crucial to discuss this side. And one of the foremost ethical concerns, one that gets a lot of attention, and rightly so, is bias. AI systems, as we've established, learn from data. The fundamental challenge is that if the historical data they are trained on contains existing societal biases, whether they are based on race, gender, age, socioeconomic status, or anything else, the algorithms won't just passively reflect those biases. They can actually amplify and exacerbate them in their decisions and outputs, often in ways that are hard to predict or control.
Right. They learn our flaws along with everything else. Can you give us some concrete examples of where that has actually played out in the real world, causing harm?
Certainly, there have been well-documented instances of discrimination in loan applications where AI systems trained on historical lending data, which itself might have been biased, ended up unfairly denying loans to qualified applicants from certain demographic groups. There was a notable early case back in 1988, believe it or not, where a UK medical school's automated admissions program was found to be biased against candidates who were women or had non-European sounding names simply because it had learned patterns from past human-made biased admissions decisions. More recently, concerns have been raised about predictive policing algorithms. If they're trained primarily on historical arrest data, which might already reflect biased policing practices, they can end up recommending disproportionately high levels of policing in minority communities, creating a harmful feedback loop.
And I remember hearing about language models or image recognition systems that produced highly problematic, even offensive results. Can they pick up these more subtle, ingrained societal biases too?
Oh, absolutely. Language models, especially the very large ones trained on vast swaths of text from the internet, are particularly susceptible. They ingest human language, warts and all. Remember the infamous case of Microsoft's Tay chatbot? It was designed to learn from interactions on Twitter and very quickly started spewing racist and sexist language it picked up from users. Or there was an incident where a major photo service's AI mistakenly tagged images of Black people as gorillas. These aren't just glitches, they reflect deep-seated biases present in the training data and potentially in the design choices. This raises a really difficult question for all of us. How do we build truly equitable AI systems when the very data they need to learn from often reflects existing societal inequities? It's a massive challenge. And some argue that the lack of diversity within the AI development field itself is also a contributing factor here.
That's a critical point.
Mhm.
Okay, another huge concern is understanding why an AI makes a certain decision. Especially in high-stakes areas like healthcare or the justice system, surely just getting the right answer isn't enough. We need to know the reasoning right.
That hits on the challenge of lack of transparency and explainability, often referred to as the black box problem. Many deep learning methods, particularly the most powerful ones with millions or billions of parameters, are incredibly effective, but they function like black boxes. They give you an output, often a very accurate one, but it's extremely difficult, sometimes practically impossible, to trace back why they arrived at that specific decision or prediction. What features did it focus on? What was its internal reasoning? This lack of transparency makes it really challenging to trust or verify their internal workings. And as you said, this is a major concern in sensitive applications like medical diagnosis, where a doctor needs to understand why the AI suggests a certain condition, or in criminal justice, where accountability demands knowing the basis for a decision.
Right, you can't just say the computer said so when someone's life or liberty is on the line. And I've also heard about AIs being fooled, sometimes quite easily, even by tiny, almost imperceptible changes to inputs. Is that a significant vulnerability?
It is a very real and concerning vulnerability. Deep learning architectures can exhibit some quite problematic, counterintuitive behaviors.
Hmm.
For example, researchers have shown they can sometimes confidently classify completely unrecognizable random noise images as familiar objects. Or, perhaps more disturbingly, they can misclassify an image they previously got right, just by adding tiny, carefully crafted alterations to the pixels that are totally unnoticeable to a human eye. These are called adversarial attacks.
So you could trick an AI system deliberately.
Yes, and this translates into potential real-world cyber threats. Imagine someone putting specially designed stickers on a stop sign that makes a self-driving car's vision system perceive it as a yield sign or a speed limit sign. Or researchers have created audio signals inaudible to humans that can trigger voice commands in smart speakers without the owner's knowledge. This leads to an ongoing technological arms race between AI attackers trying to find these vulnerabilities and defenders trying to make models more robust, much like the constant battle in malware defense. There's also the related risk of data poisoning. This is where malicious actors secretly introduce corrupted or misleading data into a system's training set, aiming to sabotage its learning process or subtly steer it towards making biased or incorrect decisions later on.
Wow, that's incredibly concerning, the potential for deliberate manipulation. And thinking about the data again, what about the human element in actually creating these vast data sets that fuel AI? Are there ethical issues simmering there too?
That brings us to data collection ethics, another really important dimension. The insatiable hunger of modern AI for vast data sets often relies heavily on what's known as human microwork. This can take the form of low-paid, often precarious online labor where people perform repetitive tasks like labeling images, transcribing audio, or verifying data, the kind of annotation that supervised learning needs. Or it can even involve implicit data generation through tasks we all do online, like solving CAPTCHAs, which helps digitize text and train OCR, or tagging friends and photos on social media, which trains facial recognition. This reliance raises significant ethical questions about fair labor practices, potential exploitation of low-wage workers globally, and also privacy concerns, as individuals often contribute their data, sometimes unknowingly or with limited understanding, to fuel the development of these powerful commercial systems.
So it's complex on many levels: bias, transparency, security, the very data itself. Given all these significant challenges, how are we as a global community trying to address them? Are there solutions or frameworks being developed?
Fortunately, yes. There's a growing awareness and significant effort being invested across academia, industry, and government to tackle these issues. It's not easy, but progress is being made. Efforts are underway to integrate ethical considerations directly into the AI design and development lifecycle right from the beginning. This involves developing clear ethical guidelines and principles for responsible AI. We're also seeing the emergence of regulatory frameworks like the EU's AI Act or aspects of GDPR regarding data privacy and automated decision-making attempting to set legal boundaries. And importantly, there's a lot of technical research focused on solutions. This includes developing fairness-aware machine learning algorithms designed to mitigate bias, techniques for improving model interpretability and explainability, opening the black box, methods for detecting and defending against adversarial attacks, and processes for rigorous algorithmic auditing to check for unintended consequences before deployment. It's definitely an ongoing journey, not a solved problem, and one that requires continuous vigilance, critical reflection, and commitment from everyone involved: researchers, developers, policymakers, and the public.
This has been a truly comprehensive deep dive. We've journeyed all the way from the fundamental principles of machine learning through the, well, profound depth of deep learning and right into the groundbreaking capabilities and complexities of transformers.
We really have. And we've seen how these technologies are not just abstract theoretical constructs anymore. They are immensely powerful forces actively shaping our world, changing everything from how we communicate and find information to how we diagnose diseases, design products, and even how our vehicles navigate.
The scale and the impact of AI are truly staggering, and frankly, understanding its underlying principles, both the potential and the pitfalls, the challenge is becoming increasingly crucial for all of us, not just tech experts. The advancements are incredibly rapid, but so are the ethical complexities and the societal implications we need to grapple with.
It's an exciting and, let's be honest, a somewhat daunting time to be alive. As these artificial intelligences become more ubiquitous, more sophisticated, learning and evolving at this unprecedented pace, it really forces us to ask, what new responsibilities do we as a society bear in guiding their development and deployment thoughtfully?
Yeah, and maybe a final provocative thought to leave you with. What might it truly mean for our own human intelligence, our creativity, our sense of self, when machines can not only understand complex language and generate strikingly creative text and images, but potentially even start to model aspects of reasoning, problem solving, maybe even hinting at emotions? Something profound to mull over until our next deep dive. If you found this exploration as fascinating as we did, we'd genuinely love to hear your thoughts and questions. Drop them in the comments below. What applications excite you? What ethical concerns worry you most? And for more deep dives into the tech and ideas shaping our world, please do hit that like button if you enjoyed this, subscribe to our show, and maybe activate the notification bell so you don't miss out. Sharing this with others who might find it interesting helps too. We look forward to unpacking another topic with you next time.